Today, we're tackling a problem that seems simple. Can a given sequence of numbers be rearranged to form an arithmetic progression? The challenge is to determine this efficiently, especially as the number of elements grows. Let's dive in. Given an array of integers, we need to return true if it's possible to rearrange the elements to form an arithmetic progression. Otherwise, we return false. An arithmetic progression means the difference between any two consecutive elements is constant. For example, 1, 3, 5 is an arithmetic progression with a common difference of 2. The most straightforward approach is to sort the array first. Once sorted, we just need to check if the difference between adjacent elements is constant. We calculate the initial difference between the first two elements, then iterate through the rest of the array, comparing each subsequent difference. If any difference doesn't match, it's not an arithmetic progression. While simple, sorting takes big O of n log n logarithmic time, which might be overkill. Space complexity is big O of 1, constant time if sorting in place, or big O of n for some sorting algorithms. To optimize, we can avoid sorting. The key insight is that in an arithmetic progression, the smallest element plus some multiple of the common difference will give us every other element. First, we find the minimum and maximum values in the array. If the array has n elements, there are n-1 gaps between them. So the common difference must be max minus min divided by n-1. If max minus min isn't perfectly divisible by n-1, or if the array has only one element, it can't be an arithmetic progression. If the common difference is 0, all elements must be identical, which is a valid progression. Otherwise, we use a hash set to store all elements from the input array. Then we iterate n times, checking if min plus I times d exists in our hash set for each I from 0 to n-1. If any expected element is missing, it's not a progression. Let's trace this with the example array, 3, 5, 1. First, we find the minimum, which is 1, and the maximum, which is 5. The array length n is 3. The expected common difference would be 5 minus 1 divided by 3 minus 1, which is 4 divided by 2, giving us 2. Since d is not 0, we proceed. We put all elements into a hash set 1, 3, 5. Now we loop. For I equals 0, we expect 1 plus 0 times 2, which is 1. The set contains 1. For I equals 1, we expect 1 plus 1 times 2, which is 3. The set contains 3. For I equals 2, we expect 1 plus 2 times 2, which is 5. The set contains 5. All expected elements are present. Since all elements generated by the arithmetic progression formula were found in our original array, we return true. The array 3, 5, 1 can indeed form an arithmetic progression, 1, 3, 5, with a common difference of 2. You'll spot this pattern when you need to verify properties of a sequence, like arithmetic or geometric progressions, without explicit ordering. If you can derive the expected elements based on min, max, and count, and then efficiently check for their presence, a hash set is often the way to go. This avoids the overhead of sorting. This optimized approach has a time complexity of big O of n due to 2 passes over the array and 1 pass for hash set lookups. The space complexity is big O of n to store elements in the hash set. This math-based approach offers a significant performance boost over sorting. Try applying this pattern to similar sequence problems. Don't forget to like and subscribe for more DSA insights.